Momentum and rotation review 4. The figure shows a bullet heading toward a block at a known speed. After the bullet embeds in the block, the combined mass slides along a horizontal surface a distance d before stopping. Derive an expression for the surface's coefficient of friction, mu sub k. What we have here is we have this bullet slamming into this block, and once that happens, that combined mass is going to begin to slide across the surface at some initial speed. Let me call that vi. As it slides, it's going to be slowing down, slowing down, slowing down. So at the end here, vf is going to, of course, equal 0. So what have we got going on? Well, lots of things. And when you don't know what to do something. I'm looking at this first interaction, and I'm thinking that when the bullet slams into the block, producing a mass that is 20 m, right? The bullet is m, the block is 19. So then when it ends up over here, it has a total mass of 20 m. Momentum is conserved right there in that interaction. And that means that the mass of the bullet times its initial velocity, that's the only thing that has momentum at first, that's going to equal the total mass, once the bullet has embedded into the block, multiplied by that initial speed that it starts sliding at, after which it will slow down, slow down, slow down. So what does this give us for that initial sliding speed? Vi is going to be 1/20th of V naught. We could write a decimal if we wanted, but that's fine. Now what happens? This thing is sliding. It's slowing down. There is friction, so we can't use conservation of energy. But its speed is changing because it started out sliding at 1/20th of V naught, and then it ends up 0. So that means that its kinetic energy has changed. And when its kinetic energy has changed, that means that we can use the work energy theorem, where the net work is equal to the change in kinetic energy. What does this right side look like? The change in kinetic energy is going to be 1/2 times the mass. Mass is 20 m. V final squared minus V initial squared. Well, V final squared is just 0. V initial squared, that's this right here. 1/20th V naught squared. V naught squared over 400. That's what the right side looks like to me. What about the left side? The net work. Who does work on this sliding mass? Well, it's not gravity, because that's perpendicular to the displacement. It's not the normal force, because that's perpendicular to the displacement. It's friction, kinetic friction. And so the net work done is going to be equal to the kinetic friction force multiplied by the distance through which it acts. And we know that friction always does negative work. So I'm going to put a negative sign in front of that, because we know that friction always does negative work. All right, what is the friction force equal to? The friction force is always equal to mu sub k times the normal force. If we were to draw a free body diagram, let's scoot that up just a hair. If we were to draw a free body diagram as this mass slides, we've got mg, which is actually 20 mg right there. That's the weight. Then we've got the normal force right there. And then since we're sliding to the right, the friction force acts to the left. And the friction force is always mu sub k times the normal force. Well, the normal force and 20 mg are equal to each other. Negative friction force is mu sub k multiplied by the normal force, which is numerically equal to 20 mg, and then there's the d that I put right there. So what do we get here? Let's kind of simplify this a little bit. I'm seeing right there, I'm seeing 10 m, and then this simplifies to be the opposite of V naught squared over 400. And we want to solve this for mu sub k. So let's see if we can do that. I'm seeing these negative signs cancel. I'm seeing the m cancel. And so what is mu sub k? Let's see. Put a 2 right there. We're going to put that in the denominator so that we're going to have 1 over 800 on that side. And then we've got d in the denominator, g in the denominator, and v naught squared in the numerator. That's what I'm getting from u sub k.